This segment corresponds to the header of the heat of liquid column in the high-pressure region saturated steam table. It represents the enthalpy of 1 pound of saturated water based on 32 degrees Fahrenheit in BTU per pound, and the value increases as pressure and temperature rise. Adding this heat of liquid to the latent heat of evaporation discussed earlier gives the total heat of steam. This relationship holds for all pressure ranges in the table. This segment is a connecting part containing only the header, and the actual numerical rows are organized in the following segment.
In this chunk, I'd like to introduce the final high-pressure section of the saturated steam properties table. This table shows how the properties of steam change as pressure increases through 3 values. First, the total heat of steam Hg in BTU per pound gradually decreases from 1181.0 down to 902.7. Second, the heat component corresponding to evaporation starts at 605.2 and eventually drops to 0.0. The point where this value becomes 0 is the critical state, where the distinction between liquid and gas disappears. Third, the specific volume in cubic feet per pound decreases sharply from 0.3450 to 0.0503, meaning the steam is compressed as pressure increases. Here, V represents the specific volume in cubic feet per pound, and Hg represents the total heat of steam in BTU per pound.
From here, I'll introduce the properties of superheated steam table. This table is organized in a grid format where the horizontal and vertical axes intersect. The vertical rows are categorized by pressure, with units in lbs per SQ in, or pounds per square inch. Each pressure row also lists the saturation temperature, or Saturday temp, allowing you to immediately check the boiling point of water at that specific pressure. This header row serves as a guide for how to read the subsequent data table.
This section introduces the low-pressure range data of the superheated steam table. First, pressure is presented in 2 forms: absolute pressure, P, and gauge pressure, P. For example, 14.696 Ia is 0.0 gauge, which is atmospheric pressure, and the saturation temperature at this point is 212 degrees Fahrenheit. At 50 Ia, the gauge pressure is 35.3 and the saturation temperature is 281.01 degrees. At 100 Ia, the gauge pressure is 85.3 and the saturation temperature is 327.81 degrees. In each pressure row, the specific volume is listed on top and the total heat, Hg, is listed below as a pair. For instance, at 100 Ia, the specific volume is 4.663 and the total heat is 1,205.7. Moving horizontally, the total temperature T ranges from 360 to 1,200 degrees, showing that even at the same pressure, increasing the temperature can raise the total heat to approximately 1637 BTU per lb at 1,200 degrees.
This part introduces the continuous values for specific volume and total heat in the high-temperature region of the superheated steam table. Continuing from the previous page, each cell from total temperature 360 to 1,200 degrees is filled with a pair consisting of specific volume on top and total heat, Hg, on the bottom. There are 2 points to note here. First, at the same temperature, the specific volume decreases as pressure increases. For example, in one temperature column, it decreases from 8.041 to 5.589. Second, in the 1,200 degree column, the total heat remains nearly constant at around 1636 BTU per pound. This indicates that for sufficiently superheated high-temperature steam, the change in heat content is small even if the pressure varies. To summarize again, V is the specific volume in cubic feet per pound, and Hg is the total heat of steam in BTU per pound.
This section introduces the medium pressure range of the superheated steam table, from 120 to 300 Ia. Absolute and gauge pressures are listed side by side. 120 Ia is 105.3 gauge with a saturation temperature of 341.25 degrees. 200 Ia is 185.3 gauge with a saturation temperature of 381.79 degrees. and 300 psi is 285.3 gauge with a saturation temperature of 417.33 degrees. There is an important tip for reading this table. You'll see cells marked with dotted lines or left blank. This is because those temperatures are lower than the saturation temperature for that pressure, meaning the steam cannot exist in a superheated state. Looking at an example with data, at 120 psi and 360 degrees, the specific volume is 3.844, and the total heat is 1201.6. If you increase the pressure to 300 psi at the same temperature, you can see that the specific volume decreases significantly to 1.6090.
This final section introduces the continuous data on the high temperature side of the intermediate pressure range table. Continuing from the previous page, the total temperature starts from 360 degrees Fahrenheit and extends to higher temperatures such as 400, 440, 480, 500, 600, and 700 degrees Fahrenheit. Each cell contains a pair of values, with the specific volume on top and the total heat, Hg, on the bottom. For example, in the 360 degrees Fahrenheit column, you can see a specific volume of 4.636 and a total heat of 1277.2. Following the same temperature column, as pressure increases, the specific volume decreases monotonically from 4.636 down to 1.7675. In the highest temperature column, the total heat converges between approximately 1631 and 1635 BTU/lb, repeatedly confirming that the change in heat due to pressure differences is small in high-temperature superheated steam.
I would like to introduce the properties table for superheated steam. This table summarizes two key physical properties of steam based on pressure and temperature conditions. The first variable, V, represents the specific volume, with the unit being cubic feet per pound. The second variable, Hg, is the total heat of steam, with the unit being BTU per pound. Pressure is expressed in pounds per square inch, or psi, and is presented as both absolute pressure, P, and gauge pressure, P. Each pressure row also includes the saturation temperature at that pressure, which serves as the reference point for determining the degree of superheat.
This section covers the low-pressure range from 320 psi to 360 psi absolute. An absolute pressure of 320 psi corresponds to a gauge pressure of 305.3 and a saturation temperature of 423.29 degrees Fahrenheit. The saturation temperatures for 340 and 360 psi absolute are 428.97 and 434.40 degrees Fahrenheit, respectively. The temperature axis, T, represents the total temperature, and values are provided at points such as 500, 600, 700, 800, 900, 1000, and 1200 degrees Fahrenheit, ranging from 360 degrees Fahrenheit to 1200 degrees Fahrenheit. For example, at 320 psi and 500 degrees Fahrenheit, the specific volume is 1.4950 and the total heat is 1215.6. As the temperature rises to 1200 degrees Fahrenheit, the total heat increases to around 1630. The reason the low-temperature cells are left blank with dashed lines is that those temperatures are lower than the saturation temperature, meaning superheated steam does not exist there.
This chunk represents the SAT temp column, which is part of the table header. SAT temp is an abbreviation for saturation temperature. It is the column label that lists the saturation temperature in degrees Fahrenheit for each pressure row on the left. The saturation temperature is the temperature at which water boils and turns into steam at a given pressure, and it serves as the starting point for defining superheated steam. Under this label, the absolute pressure, gauge pressure, and saturation temperature are aligned and displayed as a group. By subtracting this saturation temperature from the total temperature value in the body of the table, you can calculate the degree of superheat, which is how much the steam is superheated.
This section covers the intermediate pressure range from 380 psi to 600 psi absolute, containing the pressure and saturation temperature header values on the left side of the table. Gauge pressure appears lower than absolute pressure by the amount of atmospheric pressure, which is approximately 14.7 psi. For 380 psi absolute, the gauge pressure is 365.3 and the saturation temperature is 439.60 degrees Fahrenheit. For 400 psi, the gauge pressure is 385.3 and the saturation temperature is 444.59 degrees Fahrenheit. As pressure increases, the saturation temperature also rises, reaching 585.3 gauge and 486.21 degrees Fahrenheit saturation at 600 psi. The temperature axis in the body provides pairs of specific volume and total heat values in the low temperature cells, such as 500, 540, 600, and 640 degrees Fahrenheit. For example, at 380 psi and 500 degrees Fahrenheit, the specific volume is 1.3616 and the total heat is 1247.7, while at 600 psi and 500 degrees Fahrenheit, the specific volume significantly decreases to 0.7947 and the total heat is 1215.7. You can see the trend that as pressure increases, the specific volume decreases at the same temperature.
This section covers high-temperature data for the same pressure rows, ranging from 660 to 1,200 degrees Fahrenheit. In each column of the temperature axis T, the specific volume and total heat values are paired together. For example, one cell contains a specific volume of 1.6707 and a total heat of 1,342, while the next has a specific volume of 1.7419 and a total heat of 1,363.8. Even at the same temperature, as pressure increases, the specific volume decreases. As you move down the table, the specific volume drops from around 1.67 to about 1.02. In the highest column of 1,200 degrees, the total heat converges around 1,625 to 1,630 BTU. In summary, as temperature rises, both total heat and specific volume increase, while as pressure rises at a constant temperature, the specific volume decreases.
This final chunk is the variable legend presented again at the bottom of the table, along with the indication that the properties of superheated steam table continues. It reconfirms that V is the specific volume in cubic feet per pound, and Hg is the total heat of steam in BTU per pound. This is to make it clear that the definitions of the variables apply consistently from start to finish across the long table spanning several pages. In practice, you simply find a row for the desired pressure and the column for the total temperature. Then read the specific volume and total heat values placed one above the other in the intersecting cell.
Now, I would like to introduce the structure of the properties of superheated steam table. This data table is designed to allow you to directly read the steam properties for specific pressure and temperature conditions in boilers and steam equipment. The rows on the left side contain the pressure, expressed in pounds per square inch or psi, with both absolute pressure P and gauge pressure P provided. Additionally, the saturation temperature T or SAT temp is listed so you can identify the reference temperature at which steam becomes saturated for that pressure. The columns at the top list the total temperature in degrees Fahrenheit. Each cell contains two numbers. The top number is the specific volume in cubic feet per pound, and the bottom number is the total heat of steam, Hg, in BTU per pound. In other words, it is structured so that you can read both the specific volume and total heat simultaneously from the cell where the pressure row and temperature column intersect.
I will explain the medium to low pressure region data from the table we just saw. In this section, the absolute pressure P ranges from 500 psi to 1000 psi, and the corresponding gauge pressure P ranges from approximately 540 to 1000. While the saturation temperature T rises from 489.75 to 544.61 degrees Fahrenheit. This confirms that as pressure increases, the temperature at which steam saturates also rises. For example, at an absolute pressure of 500 psi, the saturation temperature is 489.75 degrees Fahrenheit. The specific volume is approximately 0.7624 cubic feet per pound, and the total heat Hg is approximately 1,212.4 BTU. At the same pressure, as temperature increases, both specific volume and total heat increase. The specific volume grows from 0.9880 to 1.5676 cubic feet, and the total heat increases from about 1,326 BTU to around 1,625 BTU as the total temperature goes from 1,326 to 1,625 degrees Fahrenheit. To emphasize again, the top number in each cell is the specific volume in cubic feet per pound, and the bottom number is the total heat in BTU per pound.
This part covers the high-temperature region and the symbol definitions of the same superheated steam table. In the section with higher total temperatures, the total heat Hg ranges from approximately 1,297 BTU to 1,620.4 BTU, and the specific volume takes values between approximately 0.5733 and 1.1360 cubic feet per pound. What is noteworthy here is that even if the temperature is the same, the specific volume decreases as pressure increases. For example, in the same temperature column, the specific volume decreases from 0.6934 to 0.5733 cubic feet because higher pressure compresses the steam more, reducing the volume per unit mass. The symbol definitions are specified at the bottom of the table. The symbol V denotes specific volume in cubic feet per pound, and the symbol Hg denotes the total heat of steam in BTU per pound. As indicated by the continued notation, this corresponds to the latter part of the data divided into several segments.
Now, I would like to introduce the second properties of superheated steam table, which covers the high-pressure region. While the previous table was for the medium to low-pressure region, this table is dedicated to higher pressure ranges. The rows similarly contain pressure, presenting absolute pressure P, gauge pressure P, and saturation temperature SAT. Temp. T. The columns at the top list the total temperature in degrees Fahrenheit. The composition of each cell is the same as the previous table, with the top number being the specific volume in cubic feet per pound and the bottom number being the total heat Hg in BTU per pound. This table is primarily used when calculating steam properties for high-pressure applications, such as high-pressure boilers or power generation equipment.
I will explain the main data area of the high-pressure table. In this section, the absolute pressure P ranges from 1,100 psi to 2,200 psi. The gauge pressure P ranges from 1,085.3 to 2,185.3, and the saturation temperature T increases monotonically from 556.31 degrees Fahrenheit to 649.46 degrees Fahrenheit. Specifically, at an absolute pressure of 1,100 psi, the specific volume is approximately 0.5110 cubic feet, and the total heat Hg is about 1,288.5 BTU. On the other hand, as the absolute pressure increases to 2,200 psi, the specific volume decreases significantly to 0.1768 cubic feet, and the total heat drops to around 1,147.8 BTU. In other words, in the high-pressure region, there is a clear trend where both specific volume and total heat decrease as pressure increases within the same temperature column. The specific volume in this section ranges roughly from 0.1768 to 0.5904 cubic feet per pound.
Finally, I will explain the high-temperature region data of the high-pressure table. This part contains values for columns with high total temperatures, where the total heat Hg is distributed from approximately 1,305.4 BTU to 1,615.2 BTU, and the specific volume ranges from about 0.2621 to 0.8716 cubic feet per pound. The data flow can be summarized in two directions. First, in the same pressure row, as the temperature increases, both specific volume and total heat increase. For example, the total heat increases from 1,371.7 BTU to 1,615.2 BTU. Second, in the same temperature column, as the pressure increases, the specific volume decreases, dropping from 0.6049 to 0.2621 cubic feet. This table is also labeled as Properties of Superheated Steam, Continued, indicating it is the latter part following the previous data.
I would like to introduce the definition of the symbols used in the superheated steam property table. This table organizes the state variables of superheated steam by pressure and temperature conditions, using two key symbols. The first symbol, V, represents the specific volume, which is the volume per unit mass measured in cubic feet per pound. The second symbol, Hg, represents the total heat of steam measured in BTU per pound. The rows of the table are divided by pressure in pounds per square inch, or SI, and it is designed so that you can read both the specific volume V and total heat Hg at the intersection of each pressure and temperature. Therefore, given any operating pressure and steam temperature, you can simultaneously check the volume and heat in the corresponding cell.
I will now introduce the saturation temperature item of the superheated steam table. At the top of the table, there is a SAT temp row for each pressure condition. Saturation temperature refers to the temperature at which water boils and turns into steam at a given pressure. The region with temperatures higher than this is the superheated zone, and the specific volume and total heat values listed in the main body of the table are read based on this saturation temperature as a baseline, depending on the degree of superheat. In other words, the saturation temperature for each pressure serves as the starting point for interpreting the table.
I would like to introduce the high-pressure region data of the superheated steam table. This section covers absolute pressures from 660 psi to 3,206.2 psi. The gauge pressure is listed as approximately 14.7 psi lower than the absolute pressure. For example, for an absolute pressure of 660, the saturation temperature is 655.91 degrees Fahrenheit. As pressure increases, the saturation temperature also rises, reaching 705.4 degrees Fahrenheit at the critical pressure of 3,206.2 psi. Meanwhile, as pressure increases, the specific volume decreases. At 660 psi, the specific volume V is 0.1575 and the total heat Hg is 1,123.8. The main body of the table is a grid structure with pressure as rows and total temperature T in degrees Fahrenheit as columns, and you read the specific volume and total heat together at each intersection. For instance, in a certain temperature column, values such as 0.2468 with 1,298.4 and 0.4023 with 1,589.6 appear.
I would like to introduce the high-temperature continuous data in the superheated steam tables. This section continues the specific volume and enthalpy values for higher temperature ranges for the pressure rows we saw previously. For example, it lists values such as a specific volume of 0.1660 with an enthalpy of 1,242.2, 0.2014 with 1,329.7, and 0.3018 with 1,574.3. At the same pressure, as the temperature increases, the steam expands, so the specific volume and enthalpy tend to increase together. Conversely, if you move down the table to higher pressures, the specific volume decreases even for the same temperature row. All values are consistently applied in units of cubic feet per pound for specific volume and BTU per pound for enthalpy.
Next, we turn to pipe flow and pressure.
I would like to introduce the calculation of the velocity of liquids flowing in a pipe. The mean velocity of a flowing liquid can be found using a formula or the nomograph on the opposite page. The nomograph is a tool that provides a graphical solution to this formula. The mean velocity, V, is calculated as 183.3 times q divided by d squared, or 0.408 times q divided by d squared, or 0.0559 times W divided by D squared times density. Here, Q is the flow rate, W is the mass flow rate in pounds per hour, and D is the internal diameter of the pipe. 4D values refer to the carbon steel, alloy steel, and stainless steel pipe data tables in Chapter 11. Additionally, for water at 60 degrees Fahrenheit in Schedule 40 pipe, the pressure drop per 100 feet and velocity have been pre-calculated for commonly used flow rates, with pipe sizes ranging from 1/8 in to 24 inches, listed in the tables. In Example 1, we find a flow rate in gallons per minute and a mean velocity in the pipe when number 3 fuel oil with a specific gravity of 0.898 at 60 degrees Fahrenheit flows through a 2 inches Schedule 40 pipe at a rate of 45,000 pounds per hour.
I would like to introduce the velocity nomograph example and the reasonable velocities for water. In the solution for example 1, the density ρ is calculated as 56.02 pounds per cubic foot, which is the specific gravity of the fluid multiplied by the density of water at the same temperature. By connecting the mass flow rate W of 45,000 and the density of 56.02 on the nomograph, the flow rate Q is read as 100 gallons per minute. The conditions for example 2 are a maximum flow rate of 300 gallons per minute and a maximum velocity limited to 12 feet per second using a Schedule 40 pipe. Connecting Q of 300 and a velocity of 12 gives an internal diameter D of 3.2, leading to the conclusion that a 3.5 in Schedule 40 pipe is suitable, with an actual velocity of 10 feet per second. Finally, the reasonable velocity standards for water are 8 to 15 feet per second for boiler feed, 4 to 7 feet per second for pump suction and drain lines, 4 to 10 feet per second for general service, and 7 feet per second or less for city service. This data is cited with permission from Crane Company as Technical Paper number 410, Flow of Fluids.
Now, I would like to introduce one of the key tables in the Engineering Data chapter of the Control Valve Handbook, the table for the flow of water through Schedule 40 steel pipe. This table summarizes the pressure drop per 100 feet of pipe and the velocity for water at 60 degrees Fahrenheit across various pipe diameters. On the far left of the table, the input flow rates are listed side by side in 2 units, gallons per minute, GPM, and cubic feet per second, feet superscript 3/s. To the right, there are pairs of columns for each pipe diameter. The left column shows the velocity in feet per second, and the right column shows the pressure drop in psi. It is important to note that the pressure drop is always based on 100 feet of pipe length. The usage is simple. Determine the design flow rate, find the corresponding row, and look at the columns for the desired pipe diameter to read both the velocity and the pressure drop per 100 feet for those conditions.
The second part of the table covers small diameter pipes, with values starting from very low flow rates. The column headers indicate the flow per second and the pressure drop in psi, and the pipe diameters follow in order: 1/8 in, 1/4 in, 3/8 in, and 1/2 in. For example, when the flow rate is 0.2 gallons per minute, or 0.000446 cubic feet per second, the velocity in a 1/8 in pipe is 1.13 feet per second, and the pressure drop per 100 feet is 1.86 psi. If the flow rate increases to 0.5 gallons per minute, the velocity in a 1/4 in pipe is 1.54 feet per second, and the pressure drop is 2.39 psi. The key trend here is that for the same flow rate, as the pipe diameter increases, the velocity decreases, and the pressure drop drops sharply. At 0.00446 cubic feet per second, the pressure drop in a 1/8 inch pipe reaches as high as 134.4 psi, but it drops to 0.526 psi in a 1/2 in pipe. The table extends to columns for 1.5 in and 2.5 inches pipes. In the row for 0.1003 cubic feet per second, you can directly compare velocities by diameter, such as 4.30 feet per second for a 3/4 in pipe and 3.02 feet per second for a 1-inch pipe.
This section is the concluding part of the first table, covering medium diameter pipes from 3/4 in to 4 inches. The structure is the same as before, pairing velocity in feet per second with pressure drop in psi per 100 feet. Looking at representative values for the same flow rate, a 3/4 in pipe has a velocity of 8.40 feet per second and a pressure drop of 36.7 psi, whereas a 1-inch pipe's velocity is 5.28 feet per second and the drop is significantly lower at 11.2 psi. Moving up one size to a 1.25 in pipe, the velocity is 3.01 feet per second with a drop of 2.75 psi, and for a 1.5 inches pipe, it falls to 1.86 feet per second with a drop of 0.835 psi. At the end of the table, a 3.5 in Pipe is listed at 9.28 feet per second with a drop of 16.7 psi and of 4 inches. Pipe at 5.37 feet per second with a drop of 4.22 psi. The title of this table is Flow of Water through Schedule 40 Steel Pipe, and it continues into the next table.
Next is the second part of the flow table, which is an expanded table to accommodate larger flow rates and larger pipe diameters. The reference conditions remain the same. Schedule 40 steel pipe, water at 60 degrees Fahrenheit, and pressure drop in velocity per 100 feet of pipe length. A feature of this expanded table is that up to 8 velocity columns are arranged side by side, allowing the velocities of several pipe diameters to be compared simultaneously in a single row. Similarly, the pressure drop side columns are arranged in parallel for each pipe diameter. The input on the left is the flow rate in cubic feet per second, and the table covers much larger flow rates in large diameter pipes such as 5 inches, 6 inches, 8 inches, and 10 inches. Because there are many pipe diameter columns, designers can broadly contrast the velocity and pressure drop of various diameters in one line to select the appropriate pipe size.
This part is the main body of the second table, containing actual values for high-flow sections. Inputs are shown in cubic feet per second and gallons per minute, starting from the row for 0.1114 cubic feet per second. In this row, one pipe diameter shows a velocity of 4.78 feet per second with a pressure drop of 2.03 psi, while a larger diameter shows 3.35 feet per second with a drop of 0.839 psi. In the 0.2228 cubic feet per second row, the smaller diameter has a velocity of 9.56 feet per second and a drop of 7.59 psi, whereas the larger diameter drops to 1.11 feet per second and 0.036 psi, showing a wide distribution. Notably, as the flow rate increases, 3 dashes appear in the smaller diameter columns, indicating that they are outside the applicable range. For example, in the 0.5013 cubic feet per second row, the small diameter columns are empty with dashes, and you only read valid values from the large diameter columns. Also, the 10 inches pipe appears in this section. At 1.059 cubic feet per second, the velocity is 1.93 feet per second and the pressure drop is 0.054 psi. In summary, as the flow rate increases, small diameter pipes become unusable, so you naturally move to the large diameter columns to read the data.